Okay, and we're back. So this is a second video about graphs and how to read them. So I went looking for some graphs that I knew of and just sort of poking around just to walk you through that little Super Mario character climbing up and down on the graph and using that as a device that we can use to interpret any graph that's thrown our way. So I've got a few here. So we've got two axes. Now, I've deliberately picked things might get confused upon a first viewing. But the intent is that you can step your way through it. So that way, when you encounter a graph that you may not be familiar with, you'll be able to cope. All right. So here's a graph. What's happening here? I see some dots. I see a green line. What's going on? So let's just imagine that Super Mario character. So these green dots are actually the plot. All right. If you see a straight line, that's usually something that a human has added to the graph to try and understand what's going on. Usually a straight line fitted to the data points is usually used to try and measure how much something is changing, right? So how much has one thing gone up uh, versus the other variable. So for example, how quickly do you hate me when I punch you more times in the face? You know, uh, some people might sort of slowly get really steamed and angry. Some people might get very angry very quickly. So that amount of sloppiness, that's what these little lines are doing. It's a way of calculating it. And I think you've done this in maths class as well, for at least my U9s have. So let's step it through. So what's going on here? What's my independent variable here? So the number of protons, Z. So there's going to be a little bit of extra info that we need to know. So for me, I understand that the letter Z is one of the ways of writing the algebra symbol for number of protons. And the number of neutrons is sometimes referred to as N, all right? So as the number of protons increases, what happens to the number of neutrons? So this is actually a graph describing the proton and neutron count for the elements of the periodic table. So as we go from a low periodic table number to a high atomic number, how did the neutrons respond? So we can see in the early stages here between 0, or technically 1, there's no 0 proton atoms. um, so from atomic number of 1 proton up to, let's say, I don't know, 20, 25 perhaps, we can see that it's going up at a steady pace. How steady is it? It looks like it's running through 0, 0 and 20, 20. That means that if I go up by 20, so if I increase the number of protons by 20, I'm also increasing the number of neutrons by 20. Okay, so we call this a 1-to-1 ratio, and it's actually proportional. If I punch you twice as hard, you hate me twice as much. It's a proportional relationship here. So if I twice as many protons, I get as many neutrons in the vertical. And then I just watch the Mario as they keep going on. So he starts off on it's pretty steep, and then it gets steeper, doesn't it? So Mario has a harder time. So what's happening here? So, well, as the number of protons increases, at first, it's not so steep. And then once we get past this 25 protons, I'm reading in between the lines here, around 25 protons on the steepness increases. Now, these are wishy-washy words. It would be really good if we could actually put some hard numbers to this. So this is something you'll have to do when you describe a graph. So you have to describe, okay, is it going up? Is it going down? When did it do this? And how much? Okay, got that? So is it going up? Is it going down? Is it going up fast? Is it going up slowly? And if you can throw in numbers, that'd be great. So I will return to this one here later. I think I'll do this one at the end, but let me just put a reminder. Reminder, first graph. You know what? That's a really tiny font. Let's just increase that. Still too tiny. All right, I'll come back to this later. So let's look at some other graphs. So, okay, here's some things that might look a bit familiar. Counts per minute. Okay, so a number of days is increasing. The number of counts per minute is decreasing. All right, so we start off with really number of counts per minute, and then as Mario climbs forward in time, it's dropping. It's dropping in the number of counts per minute. So it drops quite rapidly at first, and then it starts to taper off until it gradually approaches 0. See this little 0 line here on the vertical? It's gradually approaching 0. That's how you would describe that. This is actually a radioactive decay graph. I just don't know why they named it poorly. There should be a title up here. There should be units here. There should be things like that. A lot of things are lacking, but it gave you the rough shape. Let's continue. So here's another fancy diagram. This is one of my favorites. It tells you what phase, what state of matter does water exist at whatever temperature and whatever pressure. So you know how temperature makes the more heat makes the particles move more, and they move apart, and then they start flying apart from their attractive, forces between each other. But if you also cram them together with high pressure, you can also throw that into the mix and make them do different things. So you're mostly familiar at. So let's see here. So we got temperature on the bottom scale, and then our vertical scale is P. P is going to be for pressure, right, in atmospheres. All right. So just a bit extra reading here. If I was to give you a graph for the first time, I would expect to give you something a bit more English than just writing the letter P. All right, so we got increasing temperature going this way, and we've got increasing pressure going this way. So let's try and read this. So between 0 and 0.01 degrees Celsius, water exists in the steam phase. Is that true? Steam. No, water vapor. Sorry, I just don't. Okay, so at low temperature and low pressure, okay, that's the important thing. Low temperature and low pressure, water has to exist in water vapor form, so it's kind of being sucked away and pulled apart from each other in a vacuum, or it can exist as ice if the pressure is a little bit higher. But if the pressure is lower, it'll be water vapor. If we climb between 0.01 temperature degrees Celsius to about 100 degrees Celsius, then water tends to exist at low pressures, a water vapor still. But if it's above, I don't know, above 0.006 and roughly above one of these atmospheres of pressure, then it tends to be in this upper region of the graph, and it's in the water phase, and so on and so forth. There's just ways of reading. The main thing I want you to get out of this this exercise is that you look at the scales and then you sort of see what's happening. Okay, let's go another graph. So here's one that's probably very easy to most of us. We've got year, so that's a time axis here. We're going from early to more recent times. And then from here, what's this? Temperature anomalies. All right, so we got from negative 0.6 watt. It's in degrees Celsius. I'm reading this is why when you do a graph, it's so important to include units. It really clarifies what you mean, because temperature could be in Fahrenheit, Kelvin, it could be measuring differences in temperature, stuff like that. So we're starting off anomalies at negative 0.6 degrees all the way to positive 0.65 degrees. So what's going on here? So let's read the graph. Let's see Mario's right here, and he's going up another graph. We're seeing two different lines here. We've got the jagged one, and then we've got this darker line that's a little less jagged, but seems to follow the overall. I think this is probably just like a moving average, all right? So this is probably just a way of sort of evening out the kinks of the red lines to sort of see gradually what's going on. So let's imagine Mario starts off at 1880. The temperature anomalies was about between these two temperatures here, so maybe negative 0.2 degrees Celsius, and then he climbs down at the lowest point, which is negative negative 0.5 degrees Celsius, and that's at 1910 or a little bit before 1910. So I'm telling you how much and when. That's a really big thing when you do a written description of a graph. And we see Mario's climbing up again. Nearly climbs up to the zero line. So he climbs to the zero line at 1940. So between 1910 and 1940, the temperature anomalies is increasing from negative 0.5 degrees to 0 degrees Celsius. Then it goes down, it goes up, and so forth. So that's one graph. Let's look at another one. Sometimes you'll get a graph with multiple lines on it. That happens. And then we usually put multiple lines on a graph to save space. It's economical. Sometimes you want to compare things side by side. If you have data put on two separate charts and you're trying to line them, you're trying to eyeball them left and right, look through your left eye, look through your right eye. It's hard. So sometimes you'll put them onto the same graph, right, that measured against the same things. And then you can see how different they are. So here we can see these different lines, and they're relatively straight and they're climbing at different rates, all right? So how much the slope is going up is very different. So let's see what's going on. We've got time, so from 0 up to 600 watts, 600 seconds, okay, so 600 seconds of time. and it's about the volume of oxygen gas in milliliters, from 0 mils of gas to 50 mils of gas. All right, let's see. And then they got a little legend here to tell you what the colors mean. So room temperature with the blue line. And then we got cold temperature, which is the orange one. So it's at 8 degrees Celsius. Green one is hot temperature. All right. So and there's other one. RT, I think, is their abbreviation for room temperature. So room temperature plus a bit of water, room temperature plus a bit more water. Let's see what happens to the experiment. I don't know what the experiment is. I don't really care. It's just an exercise for us to read. So let's look at the low temperature, which is the orange one, and compare it to the green one. Let's go. So we've got at okay, it's a bit crammed in here, so I'm going to sort of make some sloppy assumptions here. So from time 0 to time 600 seconds for the 8 degrees Celsius data plot, the volume of oxygen gas climbs from 0 mils all the way up to, do they give us my mouse over it? 15.9. I'm reading it off my mouse here. 15.9. I'm also reading off of here as well to double check that that's lining up. So it goes from 0 mils of oxygen gas up to about 15 mils of oxygen gas. And we can compare that to the green plot between time 0, which has no gas, and then about time 500, right in the middle between these two bits here. It's where the graph ends. It's gone right off the chart. So it's gone from 0 mils of gas to 50 mils of gas, and it's really nice and straight. Now, straight, curvy, things like that, there's actually mathematical names for these. So here's a few. I really love this little slide here. I found it on a website. I don't remember where. I just Googled graphical relationships. I think that's the word. Graphical or mathematical. Yeah, I think it's graphical relationships, and you get these ones. So here we got the two axes here, and if the line is dead straight, it means that these two things are not related. So as I punch you more and more and more and more times in the face, the amount of money you have is probably not going to be affected. So it's going to, the money you had when I punched you once, the money you had after I punched you 10 times, it's not affected. So there's no relationship here. So it says there's no relationship. However, if you see a graph that's straight and it's climbing up from the origin point, or it might sort of cut somewhere on the y-axis as well, that also happens, then you can see that these two things have a relationship going on, and that they are directly proportional. So y is directly proportional to x. So like, as I punch you more in the face, you hate me more. So there's a relationship here, and it's going up. So if I punch you twice, you hate me twice. If I punch you 4 times more, you hate me 4 times more. Things like that. Here we've got this downward sloping one. We saw this in the, do I have it? There, we saw it in this graph here. So we call this an inversely proportional graph, all right? So y is inversely proportional to x. And that's just a way of showing like 1 over x, that sort of, these little strange things here. You don't have to know much about it now. You can learn more about it in senior and stuff like that. But it's this sort of thing where as x gets bigger, y gets less and less and less and less and less, right? Or you could read it backwards like we did with the need to pee and how close you are to the toilet. So you could always read it backwards too. Here's another one where it starts off really gentle and it climbs it very quickly. So this one here is y is proportional to the square of x. So this is an exponential or a square graph here. So how steep this sort of curve upwards can be. It's a measure of how exponential you're going at. And you also got the other ones where it starts off really steep and then it sort of tapers off, all right? So you can sort of tapering off, coming to a plateau, things like that. This one here, the square of y, the square of this number is proportional to x. So that's really fancy. Let's just say that it starts off really steep and then sort of tapers off. All right, another graph. Here's the one that comes from photography. So when the camera flash goes off, you'll get a spike in brightness, and then the bulb itself will start to, cool down, and it'll give off less and less light. And the time it takes for the bulb to sort of turn off after the flash impulse has happened, that can influence how crisp your photos can be with a flash. So some serious photographers, they really want to make sure that this whole flash duration is as short as possible. So it gets up to it and then it comes down to nothing very rapidly. And they've got different ways, like I found out the other day, that you can measure how long the duration is by measuring between these 2 points, just to go from 50% to 50% again, or you go from 10% to 10% again. But what's going on here? So I've got time, okay, it's written on the end, it should be written on the bottom. We've got amplitude, again, it should be written on the side. So as time increases, what's happening on the verticals? Here's Mario. Mario's in the corner here. He's climbing upwards. He's climbing upwards in what? He's climbing up in amplitude, right? So it climbs up very rapidly in practically no time at all. We don't have increments here to go from, so we have to sort of eyeball it. In practically no time at all, Mario climbs to 100% amplitude of the flash or brightness or things like that, and then he decreases very rapidly in amplitude and then starts to taper off, gradually approaching zero over a longer period of time. Okay, so let's go back to our first one here. Let's do a written example here. So the main things is describe, is it going up or down? Is it going up sharp or gradual? Oh, what happened there? And how much? All right, so these are the things that I'm keeping in mind when I type out. I'm going to drop this font size just slightly here. Okay. 26. All right, so what's happening here on this graph? As the number of protons increases, the number of neutrons also increases. I don't know why this computer's being like this. I apologize for the weird font jumps. As the number of protons increases, the number of neutrons also increases. And then I can go to, so it's like, is it going up? Is it going down? I can improve upon this. How do I improve it? As the number of protons increases, how much and when? So that's something I can add in right here and here. Let's do that. And then I can say how sharp it is. But let's just do overall. So let's do overall. The graph shows as the number of protons increases from 0 to, okay, looks like 100 protons is where the points sort of stop. From 0 to 100. The number of neutrons also increases from, okay, in reality, it would actually be like, anyway, if you could zoom in there, you would see that they're not 0, 0, but that's just, who cares at this point? Splitting hairs. So it increases from 0 to, how much we're increasing in the vertical? So we're increasing from 0 to 140 neutrons. That would talk about number of neutrons, so I don't have to say neutrons again. Okay, so I've done that, and I've done that. There is some detail here where it starts to deviate away from the green line, so I could start working on that in a minute. Let's keep going. So that's just one sentence, right? Next sentence, I'm just going to space them out so you can sort of see them all individually a bit better. Now I'm going to say it's going to be gradual or sharp, okay? So gradual or sharp, it'd be great if I could put the number to that, all right? So sharp, remember we talked about the slope, how we put them onto graphs to see how much things are changing? We can do a little calculation. So for slope, so slope is rise over run, all right? So how much has it risen over how much x duration? So let's look at this first region here. So we go up from like 0 to, let's say, 25. So slope starts. This is some thinking here that I would do on a scrap bit of paper or on the margin of my book. So slope start would be a rise of, looks like maybe 30 over 25. So I've risen up about 30 before it starts to deviate from the green line. And this occurs at roughly between these 2 points. Oh, it's also 30, my bad. So this would also be 30. So what's the slope there? Well, it's equal to 1. 1 what? So you know how we did rise divided by run? if you can use units in science, you just take them off the graph. So that'd be, what's the rise measured in neutrons? So it'll be neutrons per Z protons. So there we go. Or I could write in English, neutrons per proton. Yeah, it's kind of the same way that we do like meters per second, or we would do kilometers per hour, and so on. Okay, I'm just pulling them off. Like, this is the great thing about science, is they actually have meaning. They actually have units. They have things that they refer to. Okay, so what about the rest of the graph where it sort of deviates off the line? Let's calculate that one. So slope, I don't know, end. Okay, we're starting from, okay, how much are we rising? We're rising from, so I'm going to do a little numerator calculation. So something divided by something else, all right? Because I need to do a little subtraction here to work it out. I start off from that, it rises up to 140. So 140 subtract what we started in height, which is 30. All divided by how much run that has been. So it goes all the way to 100 protons, and we started from 30 protons. Okay, let's see where that takes us. So I'll do a little working here. 140, that becomes 110 divided by 70. And then I can put that into a calculator, which I have off camera. I get a slope of 1.57. Yeah, I'll round it off there. What's the unit? So 1.57 watts. It's going to be rise over run. So I'm going to take the unit from here. So neutrons per Z. There we go. So now now that I've got my thinking done, I can introduce it into my written paragraph. So I'm going to highlight. This is the writing bit. Oh no, what happened? Okay. The change in the graph starts at a steep slope of 1 neutron per proton between 0 and 30 protons on the x-axis. Then the slope increases to 1.57 neutrons per proton between 30 and 100. All right, so is it going up, is it going down? Overall, the graph shows number of protons increases, so I'm telling it's going upwards. So as the number of protons increases, the number of neutrons also increases. Have I said how much? Yes, I said it's gone from, protons went from 0 to 100, and the neutrons went from 0 to, so I've done that, and I've told it it's going up or down. Is it going up sharp or is it going up gradual? Here's my sharp and gradual. Starts off with a steep slope. A slope of 1 is actually pretty steep, I think. And then I say, so that's how steep it is at what time. And then I said for the other region of the graph, how steep it was at what time. And that's basically it, guys. I think I'll cut it there. This is probably a really long video. I apologize, but I hope this gives you a way of understanding how to read a graph and how to describe a graph. Okay, so this is the description phase. I'm doing a little bit of analysis too. So I've done a little calculation here. That's some really good points there, and then just descriptiveness as well. I'll catch you. I think I'll probably call it a night, and I'll catch you in class. See you then.